Hi friends, welcome to our YouTube channel Knowledge Academy. The main aim of this lecture is to discuss about the ISRO 2017 electrical solutions in a very detailed manner. And if you like the content of our channel, then please do like, share and subscribe our YouTube channel, and don't forget to press the bell icon button so whenever you upload a new video, the direct notifications comes on mobile. If any improvements in our lectures, then please do comment in the comment section. We will definitely include all those improvements in the coming lectures. So why to waste more time? So let's get started. So now we are going to solve the 41 question. See the question here. Ferrari Effect states that under certain conditions the sending end voltage is. So in this question they are saying about the Ferrari Effect. What is the nature of the sending end voltage when compared to the receiving end voltage? So out of the four options, option A, which is less than the receiving end voltage. So option A is the correct solution of this question. So now let us discuss something more about this Ferrari Effect. So basically the Ferrari Effect states that for medium transmission line and the long transmission line, at no load condition or the light load condition, the receiving end voltage magnitude is always greater than the sending end voltage. This is called as a Ferrari Effect. So Ferrari Effect states that at no load condition or the light load condition, only for the medium transmission line and also the long transmission line, the receiving end voltage magnitude value is very greater than the sending end voltage value. This is called as a Ferrari Effect, but not for the short transmission line. So for short transmission line, the receiving end voltage magnitude is equal to sending end voltage magnitude. This is for the short transmission line, but for the long and medium, we are going to get always the magnitude of the receiving end voltage is always greater than the magnitude of the sending end voltage for the medium transmission line or also for the long transmission line. This is called as a Ferrari Effect. Now here this is a transmission line. So transmission line has basically resistance, inductance, and because of two lines there is a small amount of capacitance. So we are going to represent with a small c. So this is a sending end voltage Vs and sending end current Is, and here we are going to connect a load. So therefore receiving end voltage and the receiving end current. So at no load condition means I am not going to keep any load condition. So therefore we can say IR is equal to 0 at no load condition. Then the current is Is here. So therefore here also current is Is. As the current is IR is equal to 0, so therefore we can say this current is also Is. So now even there is a no load, even we are not going to keep any load, then still a small amount of current Is is going to flow in the transmission line. This is called as the charging current. So this a small amount of current is going to flow even in the transmission line, even there is no load. That current we are going to say it as a charging current because of the line capacitance. Because of this line capacitance is responsible in order to a small amount of current is going to flow in a transmission line, that is called as a charging current. So now I am going to write a vector equation for this one. So Vs bar is equal to Is bar into R plus JXL plus VR bar. So by using KVL, so now here I am going to draw the phasor diagram for this one. So I am going to take VR bar as a reference. So now for VR bar, in a voltage, the current is going to lead the voltage by 90 degree. So therefore current Is and the voltage VR. So we can say current is going to lead the voltage by 90 degree. So now but here Is into R is nothing but it's a resistor. So voltage and current in a resistor and phase. So therefore if this is Is, then it will be Is bar into R. So now here there is a reactive part. So for inductor always the current is going to lag the voltage by 90 degree. As this is the current, so current should be lagging. So therefore voltage has to be in this manner, which is Is into XL. So now the overall summation of these three vectors is called as the Vs bar. So therefore this is the Vs bar. So if you see carefully, the magnitude of the Vs bar is lesser than the magnitude of the VR bar, or we can say the magnitude or the length of the vector VR bar is greater than the length of the vector Vs bar. So we can say that here this is the condition. So therefore the Ferrari Effect states that at no load condition or the light load condition, only for the medium transmission line and also the long transmission line, the sending end voltage is always lesser than the receiving end voltage because of the line capacitance. Because of line capacitance, even there is a no load condition, a small amount of current is going to flow, that we are going to call it as a charging current. Or in other way we can say that at no load condition the capacitor R is always greater greater than the inductive R. The amount of capacitive R required is very, very higher when compared to the inductive R. So because of this nature, for medium transmission line and also for the long transmission line, the receiving end voltage is always greater than the sending end voltage, and this is we are going to call it as a Ferrari effect. So now we are going to solve the 42nd question. See the question here. Shunt conductance in overhead power transmission lines is primarily due to. So shunt conductance in overhead power transmission line is primarily due to. So by which phenomena we are going to represent the shunt conductance in a transmission line? So what are the four options? Option A, leakage over the insulators, is the correct solution of this question. So let's discuss something more about this one. Basically this is a pole on which there is a small amount of insulator. Over that one we are going to keep the conductors, or we can say we are going to keep the power transmission lines. And let me assume this is a line R. So there are three lines. Out of this I am going to take only the one line, which is the R line. So now here, as this is a conductor, as it is a conductor, it is going to have some amount of resistance and also some amount of inductance. So now capacitance is because of, suppose there are more than one line, R line, Y line and B line. So R, Y, B. So these two lines are nothing but this is R and this is Y. So this is going to have a charge and this is also going to have some charge. So because of this, whenever you keep any two charges near to them and here is a dielectric medium, so we are going to say there is a capacitance between them. So this is a line capacitance. Let me assume this is a C1. So now we are going to convert in terms of phase. So therefore C is called as a line cap, or we can say phase capacitance. So because of these two lines, the charge on them is going to interact, and then there is a dielectric medium between the lines. So because of this, there is a capacitance effect. So now we will discuss about the conductance. See, because of this, let me assume the current here is I2. So now there is an insulator between a pole and also line, and also here is also an insulator. So therefore because of this, a small amount of leakage current is going to flow in air and also in the insulators. So therefore let me assume the current here is I1. So I1 is a very small amount of current which is going to pass through an insulator or an air. These both are going to act like an insulator medium, but still there is a small amount of leakage current. That current is called as the I1. So I want to represent that I1 also in a diagram. So therefore we can say a small amount of current I1 is going to flow in a conductance. As these insulators are going to have huge amount of resistance, so conductance is nothing but it is the inverse of resistance. So conductance will be very, very low value, but still the current is also very, very small value. So therefore we can say I1 is very, very less than the value of the current I2. So because of this conductance we are representing because of an insulator which is going to present between a line and also a pole, and then also air is also across the line is also going to act like an insulator, but still a small amount of current is going to leakage through these insulators. This we are going to represent in the diagram. So therefore we can say this conductance is nothing but it is a current which is flowing in a insulator medium around the line like insulators and the air. So this is the correct solution of this question. So now we are going to solve the 43rd question. See the question here. The power transmission capacity of the transmission line is. So the power transmission capacity of the transmission line is. So what are the four options? Option D, it is proportional to the square of the operating voltage, is the correct solution of this question. So now let us solve this numerical. So basically this is a synchronous generator. It is going to generate a voltage of Vs at an angle delta, and the transmission line I am going to model with the help of a reactance. But ideally there is a resistance, but the resistance is very, very low, so we are going to neglect the resistance and only we are going to keep the inductive part of a transmission line. And here at the load end, the amount of voltage received by the load end, we are going to assume it as Vr at an angle of 0 degree. Then what is the amount of power which is transferred from the active power which is transferred from the generator to the load? As the inductor, the line is an inductive part, we are going to assume it is a purely inductive. So inductor cannot consume an active power, it can only consume a reactive power. So therefore we can say the amount of active power generated by the synchronous generator is equal to the amount of active power which is absorbed by the load. So therefore we can say P is equal to the expression of the active power is the magnitude of the sending end voltage and the magnitude of the receiving end voltage, we have to do the product and divided by the amount of the line reactance into sine of delta. So therefore we can say P is equal to Vs into Vr by X into sine delta. I am going to assume that the magnitude of the sending end voltage is equal to magnitude of the receiving end voltage. So therefore Vs is equal to Vr is equal to, I am going to assume it is V. So if you substitute here, V into V is nothing but V square. So therefore P is equal to V square by X sine delta. So from this we can easily say that power transmission through a line is directly proportional to the square of the line voltage or the operating voltage. So we can say if you want to increase the power, if you want to increase the capacity of the power in a transmission line, then you have to increase the voltage of a line. Then we can say they both are going to increase. So therefore here V is called as operating voltage or the line voltage, and X is called as the line reactance of a transmission line, and delta is called as a torque angle. It is the angle between a supply voltage and also the load voltage, the difference we are going to take it down. So delta is called as a torque angle. So all these things were very important. So therefore from this we can say if you want to increase the voltage, if you want to increase the power in a line, then it is directly proportional to the square of the line voltage or the operating voltage. And this is the correct solution of this question. So now we are going to solve the 44th question. See the question here. Surge impedance of overhead transmission line is normally in the order of. So what is the surge impedance of a overhead transmission line? In this question they are asking about this one. So what are the four options? Option C, it is 300 to 500 ohms is the correct solution of this question. So now let's solve this numerical. So now we'll discuss about the surge impedance. Suppose if I am going to take a transmission line, let me assume this is the length of a transmission line, and I am going to assume that length of a transmission line is equal to infinity. So whenever I am going to assume a transmission line of very infinite length, then what is the impedance offered by this infinite length is called as a surge impedance. So whenever we are going to assume that a transmission line of infinite length, then the impedance offered by this transmission line, we are going to say it as a surge impedance, and the expression of the surge impedance is under root over L by C, where L is called as the inductance of a line and C is called as the capacitance of a line. So therefore ZS is called as a surge impedance and L is called as the inductance of line and C is called as the capacitance of line. Then we are going to know its value nature for the overhead transmission line and also for the underground cable. So basically ZS is nothing but it's a complex number, so therefore it is going to have a magnitude part and also an angle part. But now I am going to tell you only the range of the magnitude part. For the magnitude of the impedance, it can be around 300 ohm to 500 ohm for a overhead transmission line, whereas the magnitude of the surge impedance is 40 ohm to 60 ohm for a underground cable. So we can say here this is the surge impedance of the overhead transmission line is around 300 ohm to 500 ohm, whereas the surge impedance of the underground cable is nearly 40 ohm to 60 ohm. So from this we can say the surge impedance of a transmission, or we can say overhead transmission line is somewhat higher when compared to the surge impedance of the underground cable, and this is the correct solution of this question. So if you are going to assume a transmission line of very infinite length, then the impedance offered by this transmission line, we are going to say it as the surge impedance, and this is the expression of the surge impedance, which is under root over L by C. Now we are going to solve the 40th question. See the question here. An element is said to have negative resistance when. So an element is said to have negative resistance when. Out of the four options, option B, the current and the voltage curve has a negative slope. See the graph between a current and a voltage, if the slope is negative, or we can say voltage and current, if their slope is negative, so we can say definitely the resistance is a negative. Now let's solve this numerical. So now we'll discuss the difference between a positive resistance and a negative resistance. Suppose there is an element. So for this, if the graph between a current and voltage, if it has a positive slope. See, if this is a graph between a current and voltage, or we can say voltage and current, if the graph has a positive slope, means whenever the current is increases, the voltage is also going to increase, as whenever the current is decreases, the voltage is also decreasing. So we can say the slope is a positive. So therefore we can say, suppose for an element by Ohm's law, V is equal to IR, so therefore R is equal to V by I, or we can you can write which is delta V by delta I, or we can say it is a change in voltage by change in current. If the change in voltage is positive, then current is also change in voltage, current is positive. If the change in voltage is negative, then definitely change in current is also negative. So therefore overall ratio is always positive. So we can say this has a positive slope. So whenever a voltage or current graph, or we can say current or voltage graph, if they have positive slope, then we can say that element is a positive resistance. So whenever the current increases, the voltage increases, and whenever the current decreases, the voltage is also decreases for a positive slope. So we can say R is always positive. So now for negative resistance, if the slope is negative, means if one decreases, the other increases. If that is going to happen, then definitely the ratio is negative. So we can say it is a negative slope. So V is equal to IR, so or we can say R is equal to V by I, or we can say delta V by delta I. If change in voltage is positive but the change in current is negative, then the overall ratio is negative. If suppose change in voltage is negative but the change in current is positive, so we can say still the ratio is negative. So we can say whenever there is a negative slope, whenever there is a negative slope with respect to voltage or current and voltage, then we can say this is a graph of a negative resistance. It means that as the current increases, so voltage decreases, or we can say as current decreases, the voltage increases. So this ratio, whenever this graph has a negative slope, then definitely the resistance is said to be a negative resistance. So if a graph between a voltage and a current, or current and voltage, if they have positive slope, then we can say that element is a positive resistance. But if a graph between voltage or current and voltage, if they have negative slope, then definitely that element is said to be a negative resistance. So now we are going to solve the 46th question. See the question here. What are the eigenvalues of the following 2 by 2 matrix? So for this matrix we have to find the eigenvalues. So what are the 4 options? Option B is the correct solution of this question. So let's solve this numerical. So this is a matrix they have given. For this matrix we have to find what are the eigenvalues. So here there are 2 methods. The first one is the long procedure, and then we are going to do the shortcut in which we can easily find the solution. So first we will go for the procedure. So therefore now if you want to find the eigenvalues, the first you have to write the characteristic equation, which is the determinant of the A minus lambda is equal to 0. So if you do this one, we are going to get 2 minus lambda minus 1 minus 4, 5 minus lambda is equal to 0. By using the determinant of this matrix, which is 2 minus lambda into 5 minus lambda minus 4 into minus 1, which is 4, is equal to 0. So if you solve this one, we are going to get lambda square minus 7 lambda plus 6 is equal to 0. So 6 we can write either minus 6 into minus 1, or minus 6 plus minus 1 is nothing but minus 7. So therefore now I am going to write in this manner, which is lambda square minus 6 lambda minus lambda plus 6 is equal to 0, and lambda is the common between the first 2 terms, and minus 1 is the common between the remaining 2 terms. And if you do this one, we are going to get lambda minus 6 into lambda minus 1 is equal to 0. So therefore the eigenvalues are lambda is equal to 1 and 6. So B is the correct solution of this question. So we can do even this question in a very easy manner, which is the second method, which is sum of eigenvalues is equal to trace of the matrix. Trace means you have to add the diagonal elements, 2 plus 5, which is 7, and the determinant and the product of the eigenvalues is equal to determinant of the matrix. So if you find the determinant of this matrix, which is 2 into 5 minus 1 into minus 4, which is nothing but 6. So only the option B is going to satisfy this one. So if you add this one, 1 plus 6, which is nothing but 7, and if you do the multiplication, 1 into 6 is nothing but 6. So therefore only option B is going to satisfy this both conditions. So therefore option B is the correct solution of this question. So you can do, by using this method, you can solve the question in a very short span of time when compared to the long procedure. Now we are going to solve the 47th question. See the question here. Integration of 0 to pi by 2 and integration from 0 to pi by 2 sin of x plus y dx dy is. So we have to find what is the double integration of this sin of x plus y. So out of 4 options, option D is the correct solution of this question, which is 2. 2 is the correct solution of this question. So let's solve this numerical. Question they are given y is equal to 0 to y is equal to pi by 2, and also x is going to vary from 0 to pi by 2. Sin of x plus y dx dy, this is the integration that we need to figure out. So now in order to solve this numerical, first we have to know some basic formula of sin of a plus b. Sin of a plus b is equal to sin a into cos b plus cos a into sin b. So I am going to use this expression in some example. So therefore sin of x plus y is equal to sin x into cos y plus cos x into sin y. I have just expanded the sin of x plus y, and the remaining everything is same, which is dx into dy. So the first thing I am going to do with respect to integration x, So if you are going to do with respect to integration x, the remaining variables are treated as a constant. Here there are only two variables x and y. If you are going to do integration with respect to x, then y is a constant. So now y is a constant means cos y is a constant, and here integration of sin x is minus cos x plus, here y is a constant, so therefore sin y is a constant outside. Integration of cos x is sin x. So now I have to substitute the limits x is equal to 0 to x is equal to pi by 2. The remaining thing is same. So now I am going to substitute the upper limit minus lower limit. So in place of x, replace pi by 2. So cos pi by 2. So cos pi by 2 is nothing but 0. 0 into anything is 0. Again here in place of x, substitute pi by 2. So sin pi by 2 is nothing but 1. So 1 into sin y, sin y. So therefore sin y minus of. Now substitute the lower limit. Cos 0. Cos 0 is nothing but 1. So 1 into minus 1 is minus. So therefore minus cos y. Here x is equal to 0. So sin 0 is 0. So therefore 0 into anything is again 0. So here extra there is a 0 plus 0. So now plus 0 is nothing but same as this one. So therefore I have removed this one. So now minus into minus is plus. So therefore finally we are going to get integral y is equal to 0 to pi by 2 sin y plus cos y into dy. So now we are going to do with respect to integration y. So therefore integration of sin y is minus cos y and integration of cos y is sin y. So now I have to substitute the limit. So now upper limit minus lower limit. In place of y, substitute pi by 2 and pi by 2 minus of 0, substitute 0. So minus of cos 0 plus sin 0. So minus cos pi by 2 is nothing but here minus 0 and sin pi by 2 is nothing but 1. Minus cos 0 is nothing but minus 1 plus sin 0 is 0. So 1 minus into minus is plus 1 is equal to 2. So 2 is the correct solution of this question. So therefore we can say the double integral from y changes to 0 to pi by 2 and x changes from 0 to pi by 2, then sin of x plus y dx dy is equal to 2. 2 is the correct solution of this question. So now we are going to solve the 48th question. See the question here. A ROM consists of. So here ROM, it is going to consist of what are the block diagrams it is going to contains. So what are these four options? Option A is the correct solution of this question. A ROM is going to contain a decoder and also it is followed by encoder. So now we'll discuss something more about this one. So now we'll discuss something important facts about ROM. So ROM is called as a read-only memory. Only a consumer or we can say a customer can only read the data in a ROM, but he can't write anything extra into that ROM. So we can say it is a permanent memory or non-volatile memory. Means a customer cannot write anything in the ROM, but it is going to default come. It is going to contain the software which is required in order to on a computer. And even if the computer is off, even if the power is off, the data in the ROM is not able to removed. It is always stored permanently. So we can say it is a non-volatile memory. It is not going to change by the consumer or customer. Can't change anything. He can't write any data into a ROM. It is already fixed there. So we can say we can only read the data, but we can't write anything into that memory. So therefore now it is going to consist of basically a decoder and also encoder. See, decoder main function is to convert a binary system to other systems like octal systems and hexadecimal systems and decimal systems. So all these things are converted from binary to other conversion. It is done by the decoder, whereas the encoder is going to convert from other number system to binary like decimal to binary, octal to binary, hexadecimal to binary. This is the way they are going to perform. So decoder converts the binary number system to other number system and the encoder is going to convert other number system to binary. So now for a decoder there are n input lines. So based on these n input lines there will be 2 to the power of n output lines. So we can say even if n lines, it's a binary, so therefore all our input lines are going to active. So based on this, out of this 2 to the power of n output lines, only one line is going to get active and the remaining things are non-active. So based on this input data, this encoder is going to convert in terms of binary. So maximum it can have n output lines, but we are going to use only few number of output lines. So therefore we are going to general it m. So m is always less than or equal to n. It can't be a greater than n. So therefore we can say out of this only one input line is going to get active and then we are going to convert in terms of the binary format. So therefore we can say here generally the ROM is going to represent, it is equivalent to n input lines and m output lines. So based on n input lines it is going to give an output of m output lines, and this is a basic function of a ROM. ROM is going to consist of decoder followed by an encoder. So now we are going to solve the 49th question. See the question here. Which of the following multivibrator is called the flip-flop? flip-flop. So which of the following multi-vibrator is called as a flip-flop? So out of these four options, option C, bistable multi-vibrator is the correct solution of this question. So let's solve this numerical. So basically in a flip-flop, there are two stable states. One is the 0 and one is the 1. So based on the control input. So based on the control input and also the inputs, it can change from 0 stage to 1 stage, like a stable states. So based on the control inputs, we can say clock signal and the input, the output can change from 0 to 1 or 1 to 0 in a stable manner. It is going to stay permanently. If you are not giving any clock signal and the inputs are disabled, then the output will be always either 1 or 0. It's a stable state. So we can say these two states are in a stable manner for a flip-flop. But for a monostable multi-vibrator, here either we can have 0 as a stable state or 1 as a stable state individually, but we can't get both as a stable states for a monostable. But for a astable multi-vibrator, the output is going to change continuously from 0 to 1 and 1 to 0. So we can say nothing is a stable state. So we can say it is a astable, means it is continuously changing, alternating, it is going to continuously changing irrespective of the triggering input. So we can say this is a astable multi-vibrator. But for a bistable, it is going to have two stable states, 1 and 0. So based on the triggering input, the output can change from 0 to 1 or 1 to 0 and it is a stable state. So therefore we can say these two are same. So therefore based on the clock and also the inputs, the output can change from 0 to 1 or 1 to 0, and the bistable also based on the triggering input, the output can change from 0 to 1 or 1 to 0, and these are stable states. If you are not giving any triggering input, the output will be either 1 or 0 permanently, and if you are not going to give any clock input, the output will be either 0 or 1 permanently. But here, irrespective of the triggering input, the output is always going to fluctuate between 0 and 1 continuously. But here we can get only one state as a stable at a time, but we can't get both things at a same stable state. We can't get them. So because of this, it is called as a monostable. This is astable and this is a bistable. So bistable is nothing but it is a flip-flop. The category, or we can say the function of both are same because they are going to have two stable states based on the triggering or clock inputs. So this is the last question of this lecture. See the question here. Which of the following devices are required to measure three-phase balanced power? So out of this, which instrument is required to measure a three-phase balanced power? So out of the four options, option A, only one wattmeter is required in order to measure a three-phase balanced power, and we will discuss this one in a very detailed manner. So basically for n-phase system, we can categorize into two forms, which are the n-phase n wire or n-phase n plus 1 wire. The extra wire is called as a neutral wire. So now here for a balanced load and unbalanced load, for n-phase n wire system, for balanced load we require n minus 1 number of wattmeters. These are the minimum wattmeters required in order to measure the active amount of power which is consumed by the load. For unbalanced load we require n minus 1 wattmeters. So it is same for both balanced load and unbalanced load. But for n phase n plus 1 wire system, for balanced load we need only 1 wattmeter. Minimum we need only 1 wattmeter in order to measure the overall power consumed by a balanced load. But for unbalanced load we require n wattmeters are required. Suppose here in this question they are given n is equal to 3-phase system. So 3-phase system is n is equal to 3. Substitute here in all these things, we are going to get 3 minus 1 is 2, 3 minus 1 is 2, and here it is 1 and here it is 3. So for balanced load means it's a balanced one. Only these two things we require, balanced and balanced. So here its answer is 2 and here its answer is 1. So we can say the minimum is only 1. So therefore 1 wattmeter is required in order to measure the overall amount of active power consumed by a 3-phase balanced load. So here the upper two things are the 3-phase 3 wire and the below two things are the 3-phase 4 wire. So suppose for a 3-phase 3 wire, if the loads are either balanced load or unbalanced load, then the number of wattmeters required in order to measure the amount of total active power consumed by the load is only 2 wattmeters are required. So therefore the amount of total power is equal to 3-phase power is equal to W1 plus W2. So if you do the addition of these two wattmeter readings, we are going to get the amount of active power consumed by this overall load. Suppose if you are going to connect the load in a delta manner, whether it can be a balanced load or unbalanced load. See, balanced load is the impedance values is same for each and every one, Otherwise, we can say it is an unbalanced load. Means the magnitude values are, or we can say the impedance values, if they are different for each and every phase, we can say it is an unbalanced load. Suppose if they are same, then we can say it is a balanced load. So whether it is a balanced load or unbalanced load, if you are going to connect in a three-phase, three-wire system, then the minimum number of wattmeters required are 2 wattmeters, which is W1 and W2 in this method of arrangement. So overall active power consumed by this three-phase load is W1 plus W2. Whereas in the remaining two things, which are the three-phase 4-wire, the new wire is nothing but is a neutral wire. So therefore now here, for this new wire, if all the loads are balanced load, then we have to connect a wattmeter across one phase and neutral. So this wattmeter is going to measure the amount of active power consumed by only one phase load. But we want the overall active power consumed by this overall three-phase load, then we have to do a multiply by 3. So 3 times of W1. Then we are going to get the overall active power consumed by this load, and here always the Z has to be a balanced load, then only we can use in this manner. But suppose if the load is an unbalanced load for star connection, but three-phase 4-wire, then we have to use a 3 wattmeters in order to measure the amount of active power consumed by each and every phase. So one measures the active power consumed by Z1, and W2 measures the active power consumed by Z2, and W3 measures the amount of active power consumed by Z3. So if you do the addition of all these things, we are going to get the amount of active power consumed by overall load, which is 3 phase, is equal to W1 plus W2 plus W3, and compulsory here Z is a unbalanced load. So then we can consume that, we can tell that here in this question they are given only balanced load. So balanced load is nothing but here, so minimum 1 wattmeter is required to measure the amount of active power, and you have to do the 3 times of that reading, then we are going to get the overall power consumed by this three-phase load. So only 1 wattmeter is required in order to measure the overall active power consumed by this three-phase balanced load. So by this lecture, we have successfully completed the 50 questions in a detailed manner of the ISRO 2017 W solutions in a very detailed manner. And if you like the content of our channel, then please do like, share and subscribe our YouTube channel. And don't forget to press the bell icon button, so whenever we upload a new video, direct notifications comes to mobile. If any improvements needed in our video lectures, then please do comment in the comment section. We will definitely include all those improvements in the coming lectures. Thank you so much for watching this lecture. Keep smiling, take care, and bye bye.